So in this video, we're going to be looking at the Sturm-Liouville theory and how to find eigenfunctions and eigenvalues of ODEs. So the question states, find eigenvalues and eigenfunctions of x squared y double prime plus xy prime plus 3y is equal to lambda y. You're given these also conditions, these homogeneous conditions, y1 is 0 and y2 is 0. So to find the eigenfunctions, which are simply the lambdas, we see that this form of ODE is Euler-Kosher form, or Kosher-Euler form, I should say. And for the Cauchy-Euler form, we let y of x equal to x dr. Taking the derivative, so we can plug it back into the ODE, we get r x dr minus 1, and y double prime is plugging these back into the ODE, we're going to get this. Okay, and then just simplifying this further, we can factor in the x's, well, the exponents of the x's. So we're just going to have and obviously just take factoring out by the x dr and bring everything to the other side basically yields this equation. Yields x. Actually, just for proper form, I'm going to bring everything to the other side first and factor out x to the power r. So just going to look like this. And then yeah, obviously xr can't be equal to 0. So then we have this form equation. We're just going to get this, and we're solving for r in this case. So to find our solution y of x, so we're going to get that r is equal to plus or minus square root of lambda minus 3. That means our solution is going to be of this form. Y of x is a x then root lambda minus 3 plus b x the negative root lambda minus 3. So now we're going to apply our first condition, which is that y1 is equal to 0. 0 is going to be equal to a plus b, because 1 to the power of anything is just 1. So that's going to say that a is equal to negative b. Now, if we use that, we've just learned, we can write y of x as negative b x to the power of square root and factoring out of b now, it's going to be written as follows. Okay, now applying our second condition, which is that y of 2 is equal to 0. So then 0 is going to be equal to b 2 to the negative square root. And b is not, we're going to say b is not 0 because that gives a trivial solution. So we're simply going to have 2 to the power root lambda minus 3 is equal to 2 to the power negative root lambda minus 3. Dividing through everything by 2 to the negative of root lambda minus 3. We're going to get that 2 to the 2 root lambda minus 3 is equal to 1. That's 2 to the power 2 times that whole thing. Now, we're going to apply the Euler identity, which is always used in these types of questions. It's a very important identity, so I'm going to write it out. And that's the identity. Now, to be able to use in our case in particular, we're going to square both sides. And we're also going to square by n as well, or not square, but just multiply by the exponent n. So we're going to get e is equal to n pi I is equal to 1 to the power n. 1 to the power, and that's for n is equal to 1, 2, 3, etc. For any n, obviously, once the n is just 1. So what we're going to have is we're going to have e to the 2n pi I is equal to 1. That's the identity we want to use to simplify our problem. So we're going to get that 2 to the power 2 root lambda minus 3 is equal to e to the 2n pi I, which isn't that useful for us yet because we can't equate exponents. But what we can say is we can say that e to the ln 2 to the power 2 root lambda minus 3 is equal to e to the 2n pi I. E to the ln is just 1. Well, they cancel each other out, basically. So it's the same expression. Now we can equate exponents and say that ln of 2 to the power 2 root lambda minus 3 is equal to 2n pi I. And in the same way, we can say as a property of lns, we can say that 2 root lambda minus 3, we just bring that exponent down. And we're solving for lambda, which is our eigenvalue. This is now actually lambda n, because we've set it for all n from 1 to infinity, which is what we want because it's all the eigenvalues to solve our ODE. Well, for our ODE, I should say. So I'm just going to do some rearranging here. And then lambda is equal to n squared pi squared I squared divided by ln 2 squared plus 3. Now I squared is equal to -1. This is actually just going to be equal to lambda n negative n squared pi squared over ln 2 squared plus 3. For n is equal to 1, 2, etc. Those are eigenvalues for our ODE. Now we want to find our eigenfunctions, which are our functions y of n of x, I should say, which are expressed in terms of our eigenvalue. So functions yn of x expressed of eigenvalues. So from previously, we saw that y of x, this step here. So we'll use this. We now know what our lambda is. So we're just going to plug that in directly. What we're trying to find is we're trying to find our eigenfunctions, which is y of x, or yn of x, once we plug in our eigenfunctions, or eigenvalues, I should say. So we'll use that expression directly. And just to simplify our work a little bit, we'll just break it down. So root lambda minus 3 is equal to, it's going to be equal to the root of our lambda n. So that's what we're going to be plugging in. So it's just going to be root of negative n squared pi squared over 1, 2 squared plus 3, negative 3. Obviously, the 3's will cancel. The root will be simple. The negative will come out as an imaginary number I. So that's just going to be equal to n pi I over ln 2. Okay, so let's just put this back into this equation here. So yn of x now is bn x to the negative n pi I over ln 2, negative x to the n pi I over ln 2. Okay, so we're almost there. This can be simplified further, which we'll always want to do in this type of problem. And the way we're going to do this is we're going to be using the key definitions of cosine and sine. So I'm going to write these out here. These are properties of cosine and sine. So we're going to use this to try to simplify this eigenfunction expression into a way which is a lot more precise. Or not precise, I would say just easier to deal with. So obviously we're going to want some exponential functions. So what we're going to do is we're going to use the same kind of property that we used before. We're going to say that yn of x is equal to bn e to the ln x Okay. This is x to the power. I'm just going to move this up a little bit to make it clearer. Okay. And then again, we can take the exponents down to the property of the ln. So we're going to set this is equal to negative n pi I over ln 2 ln x, negative e to the n pi I over ln 2 ln x. And now we can make a direct comparison to the sign here. As we see, we can never make rearrange this to make it look like the cos because of the negative sign in between our exponential functions, but we can rearrange it to make it look like the sign. In our case, the x is replaced by ln x. If we're comparing the two expressions, this x here is going to be ln x here. And then the i's are both present, which is perfect. This alpha here is going to be n pi over ln 2, that part. And as you can see, we're dividing by 2i here, which means we have to multiply by 2i in this expression for this to hold. We can also notice that the size of the exponents. So our exponent here, the first exponent's negative, here it's positive. And so we're going to want to factor a negative as well for our expression just to make it match the sign above. So first factor the negative. Okay, now it matches the expression above pretty well. So we'll say that this is equal to negative 2i bn times sine of alpha x. So alpha is just going to be n pi over ln 2, and x is ln x. And that's basically it. We can say that this exponent here is just a constant dn. All those values are constant values. So our eigenfunctions are just going to be dn sine n pi over ln 2 ln x. And that's for n is equal to 1, 2, 3, of course. So that's part A of the problem done. Part B, which is the part where we have to employ Sturm-Liouville theorem, which is the major learning point for this problem, is find f of x piecewise smooth in terms of the above eigenfunctions. What this is saying is basically express some function f of x as a sum of the eigenfunctions we found above. In order to do this, we use Sturm-Liouville theory. So the Sturm-Liouville form is as follows. This is the contracted version. The expanded version is what we'll be using. And what we're going to do is we're going to compare this form on the right here to our initial ODE. So our initial ODE is as follows. Just as a reminder. To make an adequate comparison, it's very important to normalize our ODE. As you can see, the exponent for the y double prime in the Sturm-Liouville form is 1. Our exponent is definitely not 1, so we're just going to normalize it by dividing through by x squared. Y's are all the same y. Now we can make a comparison. So we're first going to compare the exponent on the y prime, which is 1 over p dp by d, oops, bad writing, dp by dx is equal to 1 over x. Bring variables on both sides, and we're going to give us like this. This is obviously a separable ODE, which we can solve, and it's solved as follows. That can be simplified to that, and further simplified as p of x, which is what we're trying to find, the p, is equal to cx. We let c is equal to 1 in all cases for these problems, just to make our life easy. So p of x is equal to x. What we're doing by comparing our original ODE to the Sturm-Liouville form is we're trying to find p of x, q of x, and most importantly, the weight function w of x. So we found p of x now, and we're going to use p of x to find both q of x and w, and the weight function w of x. So secondly, we're going to compare the components on the y. So we're going to have q over p is equal to 3 over x squared. Q is equal to 3 times x over x squared, because p is simply x, and that's equal to 3 over x. And finally, I'll do it to the right here, comparing the exponent on the y to the right of the equal sign, where I have 1 over x squared is equal to w over p. So the weight function w of x is simply just going to be equal to 1 over x. That's the important part of this whole problem, to find the weight function. So we found the weight function, and the weight function is relevant in Sturm-Liouville theory. So the Sturm-Liouville theory I'll write it out and then I will explain. Okay, so Sturm-Liouville theory states that given homogeneous boundary conditions and a Hermitian operator, the eigenfunctions are orthogonal with respect to the weight function on the given bounds. So for our case, to check that this holds true, we have a Hermitian operator, which you've already checked. That's just this here in the Sturm-Liouville form. That's what we've used to find W of x. Our boundary conditions are homogeneous. That says homogeneous, apologies. Okay. And it means that our eigenfunctions, which are y and of x, we found above, are orthogonal with respect to the weight function. So that allows us to make a very big conclusion, which allows us to solve the problem. So the problem, just going back to the problem, it says expand fx in terms of the above eigenfunctions. So that's basically right as a sum of the eigenfunctions. Basically, we can write the Sturm-Liouville series, which is just that f of x is equal to the sum of some constant bk times eigenfunctions. This is the eigenfunction, which we've solved before. That's called the Sturm-Liouville series. Now, all we need to do basically is find that constant coefficient bk. And this is where we use Sturm-Liouville theory. So to find bk, I'm going to write out an integral here. Integral from 1 to 2, which are our bounds, of the weight function times the eigenfunction times the function dx. That's going to be equal to. So, so we're going to have that's equal to, we know f of x is the sum. So we'll write that first. That's just going to be the sum. K is equal to 1 of bk. Now, obviously, f of x is expressed as this sum here. So we need to also account for this yk here. We're going to write the integral now. And we're going to have yl in the integral. We're going to have yk in the integral from our sum. And we're going to have the weight function as well in the integral. Now, Sturm-Liouville theory states that the eigenfunctions are orthogonal with respect to the weight function on given bounds. So these are eigenfunctions here. And they're orthogonal to each other with respect to the weight function, which is also in the integral. And by that, we can use the Kronecker delta function. So we can rewrite this as because they're orthogonal with respect to the weight function in this integrand. The Kronecker delta function again states that it's equal to 1 for k is equal to L, equal to 0 for k is not equal to L. So obviously we don't want the trivial solution, so we force k is equal to L. That's what exactly we've done here, basically. So we've used the property of orthogonality in the integral to use the Kronecker delta. And this is very similar to what you do in when solving boundary value problems, when you use the orthogonality of sines and cosines. This is the same principle, just we're using it with eigenfunctions instead. So when we use the Kronecker delta as well, we make the variable change. So this can be rewritten as BL, which is stellar constant, integral from 1 to 2, the weight function by k squared dx. And that's equal to the left-hand side, which I'm just gonna, that's this whole thing. We're solving for our constant BL. That's gonna be equal to, just by dividing through okay. So this is our equation for our constant, which goes into this sum here. We can, in an exam situation, you can apply this equation directly. You don't need to derive it using Sturm-Liouville theorem and explaining that the eigenfunctions have to be orthogonal. You can just jump straight to this equation. Once you get the Sturm-Liouville series formed, jump straight to that equation and apply it, and then your problem is going to be solved. So now we're going to actually apply this equation. So in our case, we have BK, which is the same thing as BL. That's going to be equal to the integral of 1 to 2 of our weight function 1 over x times f of x, which is in the sum as well, or which is in the integral as well, I should say, times our eigenfunction, which from before we solved it as sine k pi ln x over ln 2 dx. Now you'll notice the constant from our eigenfunctions above was absorbed in this bk constant, so we don't include the, if I go back up, we don't include the dn here. That's the numerator, and then the denominator is just going to be the integral from 1 to 2 of 1 over x times our weight functions, or our eigenfunction squared, now the top function can't be solved, or the top integral can't be solved because of that function f of x, which we don't know what it is, but the bottom can be solved. And we're going to solve this very quickly by just doing a u substitution. So I'll call this 1. And we're just going to say let u is equal to k pi over ln 2 ln x. Then du is going to be equal to dx. So obviously you can see here that we have that 1 over x and that dx in the integral already, which makes our life great. We're just going to have to multiply by ln 2 over k pi to account for this coefficient here when making the variable change. We also note that for the integral bounds, when x is equal to 1, u is equal to 0 because ln 1 is 0, x is equal to 2, u is going to be equal to k pi. So 1 is equal to the integral from 0 to k pi, simply of sine squared u du. And the integral of sine squared, it's just going to be half of the upper bounds when your bounds are from 0 to a number. So that's just going to be equal to simply k pi over 2. And obviously we need to multiply out, which I forgot to do, by ln 2 over k pi when we make that u substitution. So we're going to have k pi over 2 times ln 2 over k pi. The k pi's will cancel, and that's going to be equal to ln 2 over 2. There you go. So then your BK coefficient is just going to be equal to 2 over ln 2 of the integral on the numerator. And finally, writing f of x piecewise smooth, as the question asks, in terms of the above eigenfunctions, we're going to use the Sturm-Liouville series. We're going to write f of x as the sum bk, okay, which are eigenfunctions, and that's going to be equal to the sum of 2 over ln 2 integral from 1 to 2, 1 over x f of x. Sine k pi over ln 2 ln x dx times the eigenfunction, which is just sine k pi over ln 2 ln x. And that's our final solution.